Thanks so much, Stanford Parent Club, for the invitation, and thanks, Jade, for inviting me to join this event and share our work with you. I'm also a Stanford parent. My daughter was class of 2025, just graduated from Stanford, majored in biology. So it was interesting to kind of learn about Stanford from the other perspective as a parent. It's nice to have that experience that we all share together. For myself, as Jade mentioned, that I've been working with this area that we started, so-called electronic skin. And it's essentially you can think about it as an embodied AI or a AI system on the body, which senses information and makes decisions. And in this case, we're particularly interested in either putting these devices onto a robot body to make a robot safer, or put on human body or inside human body to understand our health. So just a little bit about kind of how I got into this to start this area of research and where I came from. Actually, I was trained as a chemist during undergrad and PhD. And after PhD, I worked in Bell Laboratories more than 20 years ago. And that's the time when we still actually, that was before the smartphone age, and televisions were still a big box. But then,
Yeah.
yes. I heard someone said something. Okay, but that was the time when we had a dream. That is to allow the grandparents to see their grandchildren when they have a phone call. But then, if there's a big television set, it's not possible to put it on the phone. So we needed a thin display. Again, that was the time Apple actually just came out with their Macintosh computer. There wasn't even laptop at the time, but it was kind of that vision drove us to come up with from my case, develop the first semiconductor that can be used to drive these kinds of thin displays. We made the world's first paper display that's bendable and foldable more than 20 years ago. So when I moved to Stanford, then what I learned from Bell Labs was one is interdisciplinary research is really fun and also necessary to solve big problems. There in Bell Labs, I could work with, I was a chemist, but I work with physicists, engineers from all different disciplines. So I decided in Stanford, I wanted to build a team that's truly multidisciplinary from all different kinds of fields. So now in my group, we have people from chemistry, chemical engineering, material science, mechanical, electrical, bioengineering, also data science, MD, PhD. So it's really fun to work with these talented students and postdocs. On the other hand, when I started in Stanford, I felt that even though bendable and foldable display was still kind of a science fiction at the time, but companies already start working on it. So I thought I wanted to work on something that's further away. And as a material chemist, then I was inspired by the materials property of human skin, which is not only flexible, but also stretchy, biodegradable, and self-healable. So I thought that if when we make electronics, instead of just making them bendable, foldable, if we can incorporate other materials properties into these electronics, then potentially we may be able to enable new functionalities that was not possible. And also, skin has remarkable sensing capability and can communicate, generate signal that can communicate with the brain. So this is a very sophisticated electronic system if we can mimic. So that's how essentially we came up with the electronic skin concept. That is to develop kind of sensory integrated system that not only have functions that is similar to human skin, but also at the same time have the form factor, the materials property, very similar to human skin. So that's what we decided to embark on when I started in Stanford. And if we can do that, then I see that we can move electronics closer and closer to human body, from computer to smartwatch. Already we can see that trend now is happening actually in real world, and also human machine interface and neural probes now is really moving electronics inside the body. So I think this general direction is something that already, even though early on when we started, it again seemed to be a science fiction, but now it's really happening in our everyday life. So what we see is if we can build such electronic skin, then we can allow robots to work more safely together with human and collaborate with human. And in the area of human health, then if we can get close to the human body and inside the human body, that's where the information that we need to sense about human health really lie at. And in those cases, the electrical signal and chemical signal that regulate our human health measured over the entire body would be what's needed to really understand human health. And there we need devices that are comfortable, invisible, imperceptible, biocompatible, and also be able to measure information autonomously. So basically what we predicted more than 10 years ago was that such electronics, if we can realize them, they will get closer onto the body and inside the body. So now I want to talk a little bit on the technical side and also make a distinction between flexible electronics and these e-skin or skin-inspired electronics. Actually, for materials, when we characterize their mechanical properties, there's this parameter so-called modulus that is used to characterize basically how much force is needed to stretch a material. So things like silicon wafer and a lot of the rigid plastic material, you have to use a lot of force. You may even break it, but it will not extend its length that much. Or some plastics, you have to use a lot of force in order to stretch them. But on the other hand, so those are high modulus material. But on the other hand, there are gels or rubber bands that you don't need to use much force. They can already stretch. So those are low modulus materials and basically skin-like materials. And if you look at the modulus of our organ, brain is super soft, kilopascal, and skin is also in the hundreds of kilopascal, and muscle is more stiff, 500 megapascal, and the bone is very stiff in the gigapascal range. So most of the inorganic materials, such as silicon, used for our traditional electronics, microelectronics industry, the modulus is in the hundreds of gigapascal, even going into terapascal, so extremely rigid and stiff. And so even for these plastic, most of the plastic we use in daily life, their modulus are also in the hundreds of gigapascal. So these materials, you can make them really thin, like a paper thin. Then they can kind of bend, so that's flexible. But paper can still cut into tissue, soft tissue. That's because these high modulus materials still, their edges are very sharp. So as a result, if they are implanted inside the body, they can cut into the tissue and induce scar tissue formation. And also, if they are mounted on the surface of the body, they can constrain the movement. So therefore, the type of materials that we try to develop or work with are these soft materials that has modulus with comparable level with those of human tissue, more in the kilopascal and the megapascal range. So the biggest scientific challenge that we face is normal electronic materials are like silicon, very rigid and brittle. But in our case, we need these new electronic materials that are as soft as jelly, but at the same time, their electronic properties are as good as those used for our current electronics product. So this is a very tall order to put on new materials, and this kind of materials did not exist before. So that became our really fundamental core aspects of our research. That is to understand from molecular level how we design these molecules so that they can be as soft as jelly, but as good as silicon. And if you look at these molecules from atomic level, it's no surprise that you see polymers are chains of atoms all linked together. So they can bend and fold and adapt to different surfaces. That's why they can stretch. They can also reform, break bonds and reform the bonds. But silicon has this very rigid lattice structure and it's crystalline. It determines why it's very brittle. But at the same time, electronic property is great. But the polymers, they're usually insulating and not good electronic materials. So we have to really figure out how to make polymers to be semiconductor and good conductors. And over the years, we figured that out, but then they couldn't stretch. They were still brittle and cracks easily. There was a very important kind of really important breakthrough for us on the fundamental level 10 years ago. That is, we found that these semiconductor molecules or conductive molecules, we can induce these nanostructures to form by using a soft elastic matrix. And then when they form these nanostructures, so they basically form essentially like a fishnet structure, but they are interconnected. So then we got some unexpected result that we saw a boost in the ability for these molecules to actually they conduct better, and they were better semiconductors for making integrated circuits. But at the same time, we could tune these matrix so that we can add a lot of new functionalities into these electronic polymers that were previously not possible. So we make them stretchy, we make them soft, we allow them to have scratches or sometimes there's wear and tear when the materials are being used. Then we allow the chemical bonds to reform again to self-repair. And also for biomedical devices, we figured out how to make some of these materials to biodegrade so that they can become also not only more biocompatible, but also at the same time for certain implantable electronics. So we may not want the electronics to stay around forever, then they can self-degrade. And then finally, to make circuits and complex devices, we also need to pattern these materials into small structures so we can incorporate all those functions into the high performance electronic material. So that's really the basis for many of the work that we're doing these days. So then in terms of sensing, that was something that we started to look into very early on as well. We wanted sensors so that it can mimic a human sense of touch. But then we found that most of the materials available or devices that could already be available, they are either made with very large structures and also not even flexible and can break easily. Or if we get flexible materials, they don't compress that easily. Once they compress, they don't bounce back. So we came up with this pyramid-like structure. So basically, imagine this is the kind of really zoom in into the touch sensor, the sensors that can sense or mimic human skin capability for sense of touch. If we really zoom in into our device, we make these pyramid structures that these pyramid structure can easily get compressed with very, very small force. And then when this compress, then we can measure it out in terms of electrical signal, whether it's the capacitance or in terms of electrical conductivity. So that was the first time that we could actually, or for the field, to have a sensor that can start mimic sense of touch of human skin that even exceed the sensitivity of human skin. For example, to test, to feel the landing of a butterfly on a surface of electronic skin that with a very gentle movement of insects can even be detected. So that became our basis for also different generations of electronic skin with the initial sensing modality is to mimic the pressure sensing, shear sensing, and the temperature sensing of the human skin. So that was our earliest sensor. And then as time goes, we slowly kind of miniaturize them. And also we add computing function into our electronic skin. And then more recently, we now are able to also make these electronic skin to have a resolution exceeding that of human sensing capability. So this array we made here actually can read Braille pattern designed with blind patient or individuals who use those patterns to recognize or to read. In that case, usually one would read one letter at a time. But now with this electronic skin that has extremely high resolution, then with this small region, we could read multiple words at the same time. So you can imagine much faster sensing of the information, or this could even be another way of inputting information for human to add new capabilities. And then I said on-body AI. To have AI, it's not possible without computing capability. And the computing requires integrated circuits and microprocessors. So these will not be the kind of the same level of information processing capability like the NVIDIA chip or Intel microprocessors. But imagine these are, or think about those chip, NVIDIA chip is the big brain. These would be the small brain that allows the devices in the local region, like if it's for the robot hand or a sensing patch that's on the surface of the body or inside body, there's a small brain that can process the local information very quickly instead of sending all the raw data to the big brain, which will consume a lot of power and a lot of computing, also computing power and time for the big brain to process everything. So these small brains can do the local processing and then talk to the big brain. So this will allow the entire sensing system to work much better together. So then that also is something that we have been developing in the group by making these integrated circuits, turning them from these rigid silicon-based to our soft material-based by developing not only the materials, but ways to make these small transistors and make them into integrated circuits. So now, with these capabilities, now we start to looking at some interesting data we can start to collect. For example, these different dots is from our electronic skin that has the size of human hand that can capture the signal of the person grabbing different objects or interact with the surroundings. So the signal from these, you can already even see that when we have lots of sensors, then visually you can already see the difference of the signal. So these will allow training of the AI algorithm much easier to train for the algorithm to be able to tell what kind of object our hand is interacting and even get the details on the softness, texture, and other information about the object. So imagine not only for the robot to be able to have more direct knowledge about the objects that they're interacting with, but imagine maybe the surgeon teaching new student in the medical school about surgery and other training, then this will allow the students to be able to precisely trying to mimic the procedure similar to an expert. And you may say that, oh, why can't I use a camera to just see the object? The thing is, with camera, it works well with something with a defined shape and size, and you know the weight and it's predictable. But if in real world, there are many, many objects that are deformable, like that piece of toy that you just saw, when there are deformable objects, then the deformation is hard to predict. And just using camera is difficult to be able to capture all the details to provide instruction for the robot to be able to act quickly to perform tasks precisely. As human, we can see, we can feel with our hands. So that's what robot is also needed in the future. But then for human health, we not only need kind of sensors that senses from the surface of our body. We can potentially maybe map the brain wave from the body, the electrical signal from the muscle to be able to tell the movement of the person. But then the signal that can be measured from the surface of the body is still limited. That means if we want to measure inside the body, we need to go inside. But going inside, having the large 2D electronic skin sheet will be very difficult to implant because the area is too big. It will cause a lot of the surgery will cause a lot of damage to the patient and also require a long time for recovery. So for most of the surgery, actually one-dimensional fibers are being used for such kind of minimally invasive surgery. And but in this case, we still want these 1D structure, 1D fibers that are inserted into the body to be very thin, hair thin, so that the person may even hardly feel it. Or if it's inside the brain, they are soft, they will not cause damage to the brain tissue. But we still want to have many sensors and also to have capability to sense, stimulate, or actuate all in this hair thin structure. And be able to measure things beyond the electrical signal, but also neurotransmitters, hormone, and all these information that's relevant to human health. But if you look at the state of art, such kind of probe, this is the most advanced neural probe that's still not yet ready for human usage. Now, the most advanced one is of such probe that can measure thousands of electrical signal from the brain at a single neuron level in the deep brain. This is only now possible for large animals. And part of the reason is this probe itself. It's actually made with silicon. If you zoom in, you can see it's a very rigid probe. And it's hair thin. The advantage of using silicon is that they can use the most advanced technology that's used for making a NVIDIA chip to essentially build such neural probe so that these electrodes you see here, they can measure single neuron resolution. But to have thousands of them, there are going to be many, many wires in this probe. So these wires have to be ultra small in size and have to fit all in thousands of wires, all have to fit in this hair thin structure. That's why they need to use the most advanced microelectronics fabrication. So it's very costly to begin with, and very challenging to make. But also at the same time, you can see this is made with rigid silicon. So not to say that it may generate some scar tissue, but also at the same time, there's the danger or risk of this break, then that would be detrimental. So in our case, actually, we came up with this new way of making sensing fibers. So basically, we have this 2D sheet, or in a simple word, we make electronic skin on a flat surface. We just roll it up. So here there are sensors. So these triangles are some sensors that can sense the chemical signal on the surface. And then these wires are the interconnect, wire them out. You can see just a few sensors can have many wires. But we can roll them up so that these wires are all embedded. And the embedded inside the fiber, and the sensors can be placed not only on the surface but also in the fiber. So this can allow us now to make really high resolution sensors and incorporate hundreds or even thousands of sensors. So essentially, this is just a jelly roll, kind of rolled up jelly roll. And these layers, you can see layers, and these dark regions are the electrodes that's going across the fiber. On the right is the brain neural probe that we have made using this method. So this one is I guess to test the feasibility of our probe for sensing in the brain. First, we have to test in the mouse, and then slowly go to larger and larger probes. So for the mouse, we make this probe has most of the sensors are on the tip because the mouse brain is only a few millimeter in size, very small. So the probe has a sensor concentrated on the 1 millimeter region with 32 or 64 sensors here. And the width is about the width of human hair. And we have demonstrated that these sensors can indeed record single neuron, and also even be able to now, because these are soft probes, so they can bend and they don't damage the tissue. So we can now even insert in regions that are pretty previously difficult to measure. Such as in the brainstem near the neck, and also through the face to access some nerve kind of behind the mouse to measure new information and perform stimulation to treat disease. And then these probes are also very soft. So now it enables new possibility to implant these probes or place these fibers inside the intestine. There's you may heard about this talking about the gut-brain axis. The brain will control our periphery, but also our gut communicate back to the brain. If we are not eating well, or there's an immune system issue, then the gut will send through the vagus nerve to communicate with our brain that may impact our mood or mental health. And also now people are finding even memory is related to the gut-brain axis communication. So these soft string can actually be placed inside and allow the animal to freely move around and without anesthesia and be able to perform sensing. So currently we are making a pill to hopefully deliver these sensors inside the intestine without having to do some surgery. So in short, now we have basically now two powerful tools in our hand. One is electronic skin for measuring large area. One is neurostrain that measures really high density, high resolution, can go inside the body, into the brain, into the gut, or into other organs. We can measure electrical signal. We can perform electrical stimulation. We can measure neurotransmitters, hormone, and expanding these to also other chemicals, physical signals such as pressure, temperature, strain for robotic application, but also relevant to health. And they can be used for a variety of different locations on the human body, and in addition to used for robots. So going towards the future, what we are really excited about is that now we can have probes that understand the brain. But of course, it's very difficult and very invasive to put a probe into the brain. But if we can understand from measurements in the peripheral, by having one neurostrain for the interstitial fluid, but measure beyond the glucose, the pill go into the gut, and electronic skin measuring the muscle information. And all of these are reflection of what our brain is doing to control our peripheral. So if we can measure all this information on the peripheral from our organ, from our body, that will allow us to first understand our health, but also they allow us to have a way to essentially peek into the brain to know what our brain is doing and how our brain is doing. So this correlation is something that still is a holy grail, that there are a lot of understanding and scientific research to be done. So we're very excited now that we're developing all these tools. So we hope to help advance that understanding. And also to do that, we cannot just kind of have an individual group working on it. There needs to be people working together. So that's why 10 years ago, I established the Stanford Wearable Electronics Initiative to link people from all different fields and leverage the strengths of Stanford in terms of hardware, AI data science, and strengths in human health and robotics, and across different schools, School of Engineering, School of Data Science, and also School of Medicine, to all work together to have a initiative and center that can connect the people and empower faculty and the students to work on bigger problems and the more complex problems. And with the initiative, we also hope to accelerate the development of ideas from the lab to validation of concept, prototyping, and eventually get them really into the hand of patient, into the hand of people who could benefit from them. So the center also serves the role to raise funding to help support these different kinds of research internally, especially collaboration between various groups. Another activity that I'm involved in is to co-chair the Taiwan Science and Technology Hub with our Taiwan alumni to aim to connect, enable, and empower researchers, scholars, and also people from industry to collaborate together and to further advance research and development. So with that, I will close my talk and happy to answer any questions, and also, of course, also welcome people who are interested in working with us to also contact me in the future. Thank you.
Great. Thank you so much, Professor Bao. That was an enlightening talk. So much new technology. I'm just flabbergasted. So thank you so much for that. We do have questions in the chat, and I'll moderate some of the questions. I've sequenced a number of questions, hopefully in some kind of order that makes sense. The first question is, will the e-skin, the electronic skin, be able to sense characteristics beyond pressure sensitivity, such as temperature, moisture, or salinity?
Yeah, so for e-skin, there can be many sensing modalities. We focus on a subset of those, but sensing humidity is something that's definitely doable. Salinity is another possibility. We have not spent time on it, but it's possible to, for example, measure the ionic conductivity to know the salinity. And there are also recognition kind of materials that can be incorporated into these e-skin to recognize whether there's sodium ion versus potassium ion concentration change. Those are all possibilities. Yeah.
Great, thank you. The next question is that in the spirit of startup culture here in the Bay Area, and for translating science to patients and consumers, what do you see as the most persuasive consumer application of your research over, say, next 5, 10, 20 years?
Yeah, so one area is of course, pretty obvious, and right now also there's a lot of demand for it is electronic skin for robotic applications. For humanoid, there's no question that the humanoid robot will need a way of sense of touch, just like human, but also at the same time, there are many other robotic applications. For example, robots for assisted living to help elderly patient, or robots in the hospital to assist the nurse, or robot in the manufacturing setting to perform heavy duty or more difficult, dirty, and difficult work, or some work that require super high precision that might also be difficult for a human to perform. So there are a lot of such needs these days in the robotic area. And then in the health area, we already see that continuous glucose monitor on the market and its benefit. Then there are additional ones that I think is getting very close, getting to the verge of ready to, I think, go into more development stage. Things like sensors that sense cortisol, which is a stress hormone that can be linked to mental health. That would be very useful. And also sensors related to our immune system that could be very useful to have continuous measurement. So those are, I think, also getting closer to be translated. And going inside the body, I see that the neural string for various robotic surgery to have these sensors incorporated during robotic surgery or as guiding wires for various applications. Those are things that I think also may be translated in the more near future. Ultimately, I think going into the brain would be possible, but it would be a much longer pathway to get there.
Got it. Okay. A couple more questions, if I may. Many systems now rely on fingerprint authentication for access. Do you think eSkin could potentially be used to replicate somebody else's fingerprint or facial feature? In other words, does the eSkin itself have a unique identifier?
Well, eSkin can potentially read fingerprint and then allow what's read to be displayed or displayed on a screen or interpreted by the computer. The eSkin, we haven't thought about kind of generate some fingerprint like patterns with eSkin. But you can imagine some kind of identification may be incorporated into eSkin that using various combinations of features or information that's stored in the eSkin. So if that's the question, I guess can one identify a eSkin based on some unique feature or information stored in there, then that's definitely possible.
Okay, great. Another question from a parent is, are there wearable skin-based devices for brain diagnostics? I think you mentioned that in your talk for mental health, perhaps using sensing technology to detect when a patient is approaching a crisis point.
Yes, that's right. There are groups working with, for example, EEG device to measure the brain electrical signal directly from the surface of the body. The accuracy still needs improvement, but that would be another way to and relatively direct way to reflect the state of the brain. But frequently, multiple different signals combined together can be used to also understand the state of the brain. As I mentioned, the periphery actually is controlled by the brain. It's a reflection of how our brain is doing. So, for example, if there's many neurodegenerative disease, the initial sign is the motor function of the person might already be degraded. And if the pattern, how that pattern is correlated to the brain degeneration, then that could be another way to monitor over time whether there is some degradation of the brain. But those are things that are yet to be, the correlation is yet to be established. Now with new tools that is something I think will become possible. And related to mental health, also in addition to directly measure the brainwave, there are combinations of sensing signal. For example, cortisol combined with heart rate variability, breathing, and also skin conductance can be a way to potentially predict whether the person may be suffering from anxiety, crossing to depression or severe depression. So those are, again, things that still need more studies to get correlation. But tools are starting to become available.
Great. And as a follow-up to that, one of the parent was asking if you have any collaborations or grants with Neuralink. This is a company, Elon Musk, developing brain-computer interfaces.
I have students working in Neuralink. I don't have a current collaboration with them. Their probes are for probing on actually the surface of the brain. It's not for deep brain. So it it is easier for commercialization. But overall, anything that needs to be implanted into the brain is very challenging for translation. So I hope them successful, because that will be the first such implanted probe that actually is used commercially. There are other neural probes only approved for research. They are not FDA approved. So hope Neuralink can get there.
Okay, we're going to switch gears a little bit. We've been talking a lot of science and STEM. One of the questions from the parent is, what unique contributions can non-STEM majors make to interdisciplinary team science, as you've described, both during their time at Stanford and after graduation?
Mm-hmm. Yeah, I think people coming from different disciplines can bring a lot of new perspectives. And now in STEM, the goal for research is to be able to address fundamental challenges, but at the same time, these by developing new science and technology understanding to impact society. And so those are problems related to, I talked about human health, robotics, manufacturing, but also energy, environment. Those are all big areas that STEM researchers are trying to make impact. But then to make a real impact, we also need to understand the socio-economical implications, policy, and various other aspects to really have a solution that is potentially scalable and also a solution that people will want to incorporate in their daily life. And also people may be concerned about privacy and ethics issues. So these are things that I think many from other disciplines can actually help those in the STEM area to have more discussions and also even be aware of those potential kind of factors to consider down the road if we have a great technology.
Great. Okay, I see that we're nearing the end of the hour, so I'm going to ask one final question. Given your unique perspective, both as a Stanford professor and a Stanford parent, could you share any surprises or stories about how you communicate with this generation of exceptionally talented students?
Well, I think the fun thing about working with students is that they're so creative, so excited passionate about new things, and really wanted to solve problems. And I think my views of things frequently get new input by talking with students and working with students. So now, especially with new tools of AI, now I find that it's even more important to and also I see a clear change in the kind of the students coming in, their background seems to become a lot of them have some capability of coding, computing, and then plus something else. And that's really exciting. And even my PhD students who are just a few years more senior, But then I can see already their background are very different and training are very different from the current ones in the undergrad class. So that really, I don't have a conclusion yet, but that really makes me think about in research how I can best take advantage of all these talents that come with a very different type of preparation and interest and make the research most productive.
Okay. Well, thank you very much for this amazing talk. I think we all learned a little bit more this morning. And as a small token of our appreciation, the Stanford Parents Club is delighted to give you one of our signature jars of apricot jam.
Oh.